Okay, we are now going to do a numerical integration free response question. I'm going to see how far I can get without a calculator here, and I honestly don't remember what year this is from or what calculator they would have had access to. But the first thing I want you to notice is they give us data. They do not give us the function. They don't give us an equation. So none of this can be determined from the powers rule, the product rule, any of the antiderivative rules, U substitution. This is only going to be involve basic geometry and algebra, honestly, pre-algebra mostly. But you've got to understand the concepts. So let's start. Question A. Well, first off, let's see what's going on here. The graph of the velocity v of t in feet per second of a car traveling on a straight road for 0 to t to 50, I guess that's time in seconds, is shown above. A table of values for v of t at 5-second intervals of time t is shown to the right of the graph. Okay, A, during what intervals of time is the acceleration of the car positive? Okay, if your graph is a graph of velocity, and only if your graph is a graph of velocity on the y-axis, then for this graph, acceleration is the slope. Acceleration is the slope. Why? When I say derivative, you should think slope. The derivative of velocity is acceleration. That's worth writing down again. The derivative of velocity as time passes is your acceleration. Acceleration is your change in velocity. Derivative means slope. They're literally just asking, at what points on this curve would a slope of a tangent line be positive? Another way to think of this is, when is the y value on this graph increasing? Because as we've discussed before, a graph can only increase if its slope is positive, if the slope of its tangent line at every point along that interval of increase is positive. So it looks to me like the velocity of the car, and therefore the y value of this graph, increases from about 0 to 35, and then again from about 45 to 50. So I would answer this as the acceleration is positive over the interval 0 to t to 35, and so I guess I should make that intervals 45 to t to 50. It looks like 0 should be included in that. I mean, it's not starting with a slope of 0. So it looks like this car was moving pretty quickly right away, but I would not include, definitely would not put little equal signs under t equals 35 or anywhere here, because our graph, at these peaks and valleys, the car should neither be decreasing nor increasing. The acceleration is not positive or negative, it's 0, because that's where the horizontal tangent lines are. It's an easy one to overthink. It's really just look at it and determine what the slope is doing. Okay, let's go on to part B. For part B, find the average acceleration of the car in feet per second squared over the interval 0 to t to 50. Okay. When they say average acceleration, in terms of graphs in general, they mean average rate of change. An average rate of change is just slope. For the average rate of change, well, in general, it's y2 minus y1 over x2 minus x1. Well, on this graph, y is velocity and x is time. So that would be v2 minus v1 over t2 minus t1. And the period they're talking about starts at 0, 0 and ends at 50 seconds on the x-axis and 70 seconds on the y-axis. They literally just want the slope of that line from the beginning to the end of the interval. That's all. That would be the average rate of change of velocity, and that would be same as the average acceleration. They're not asking for an instantaneous rate of change. If that's what they want, they have to say instantaneous, or they have to say first derivative, and they don't give you an interval, they give you a point, because an instantaneous rate of change can only happen in an instant. So it looks like they're only asking me to do 70 minus 0, final velocity minus initial velocity, over 50 minus 0, final time minus initial time, which is 70 over 50, or 7/5 feet per second squared. It did not say to use the units, but it mentioned the units in the problem. I don't remember from the scoring guide whether that's going to be a point off or not, but get in the habit of writing it. Okay? Another easy one to overthink. They literally just wanted you to do y2 minus y1 over x2 minus x1 and put some correct units at the end. Okay, going on to part C. Find one approximation for the acceleration of the car in feet per second squared at t equals 40. Okay, at t equals 40, this is your hint. That is at an instant. So they want instantaneous, which means derivative. Now, they don't give us anything to derive, though. There's no equation here. So we're still going to have to approximate. In addition to numerical methods of approximation, you've got one numerical method for derivation. You've been doing it since pre-algebra. It's finding the slope. So there's two ways you can do this, and the College Board definitely used to give credit for both ways, but I'll double check what they're doing this year. But to find out what's happening at t equals 40 when you don't have an actual equation to derive, you can't take the derivative and plug 40 in. We have to look at the points around 40. And there's two general strategies here. One of them is ignore 40 and say that the acceleration at 40 is just approximately the slope from t equals 45 to t equals 35, or vice versa. So I'm going to put, well, first off, I'm going to write with something more permanent. I'm just going to find v2 minus v1 over t2 minus t1 again, but the times I'm going to use are 45 and 35, which means the y's that I have to use, the y values are 60 and 81. And that's going to get me negative 21 over 10, or negative 2.1 feet per second squared. For part D, I'm sorry, not for part D. The other way to do part C is you could say, you could find, or you could find the slope from 35 to 40. Do 40 minus 35. On the bottom, these are your two times. And on the top, that means you would do 75 minus 81. This gets you negative 6/5. Then we find the slope again, but now we do it from 40 to 45, which is 45 minus 40 on the bottom, 60 minus 75 on the top. And that gets me negative 15 over 5, or negative 3. If you average these things, negative 5 plus, well, that's negative 1.2. The same thing as 6/5. If you average these things, you get, well, first you add them together, you get negative 4.2. To find the average, you do negative 4.2 divided by 2. In this particular case, you get the same thing. That will not always happen with all data sets. It's kind of a coincidence on this problem. It was actually, I think, one of the rare times where the College Board tries to be a little bit nice and says, hey, you might have learned two different ways to approximate derivatives numerically. And we're going to give you a problem where, for once, the trick works in your favor, and whichever method you pick will work. Hopefully, more recent problems, they're a little more clear about what method they want you to use. Keep in mind, again, other than having to know the difference between average and instantaneous rate of change, we've done no actual calculus, not in our calculations anyway. All right, part D. Approximate the integral from 0 to 50 with the Riemann sum using the midpoints of 5 subintervals of equal length. Using correct units, explain the meaning of this integral. Okay, well, our intervals are going to be 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50. You got 50 seconds divided into 5 subintervals of equal length. That means each subinterval will be 10 seconds each. All right. Looks like, okay, now what I don't even necessarily need to draw rectangles on the graph, because the y value at the midpoint of 5 and 10 is given. It's 12, because 5 is the x value between 0 and 10, and the y value that corresponds to that 5 is 12. The y value at the midpoint of 10 and 20 is whatever y value is above 15. That's given on the table as 30. The y value at the midpoint of 20 to 30 is the y value that corresponds to 25 on the table. That's given as 70. These are the heights of my rectangles that I'm going to use to approximate this area. The midpoint y value that is right above 35, which is the midpoint between 30 and 40, seems to be 81. The last midpoint, the last y value corresponding to the x value right in the middle of 40 and 50 is 60. So that lines up with 45. Now, all of these subintervals have a base of 10. So I'm adding up, I'm finding the area of 5 rectangles. Each one has a base of 10 times a height of 12 or a height of 30 or a height of 70. This car was really accelerating between 20 and 30 seconds. With a height of 81, and lastly, with a height of 60. Add these up. It's not that hard. Most of you should be able to do this without a calculator. I'm going to leave that calculation to you guys for later. And again, we've done no actual calculus in the analytic algebraic sense of we haven't used the product rule. We haven't used the powers rule. We haven't used use substitution. We haven't taken a derivative or an antiderivative at all. It's all just numerical approximations. Now, this last bit, using correct units, explain the meaning of this integral. Okay. I had a student, I might have mentioned this to you guys before, wrote a beautiful paragraph in response to this exact practice question on a test. I gave this on a test one year. It's fantastic. It described exactly what an integral was, how it worked. It mentioned Riemann rectangles. It even mentioned other aspects of the historical origin of it that the student remembered from class. And that student got no points because he explained the meaning of every integral. What he didn't do was explain the meaning of this integral. And what this means is the integral from 0 to 50 of v of t dt in this specific case is literally just how far the car went in feet. Now, on an actual test, yes, you would have to figure out this calculation, find that number. But to answer the second part, using correct units, explain the meaning of this integral, you just have to say it's how far the car went. And since they ask for correct units, you have to do so using the word feet in there somewhere. That's all. Anything else you say is a waste of time on your part during the test and on the part of the grader, who is very quickly trying to go through and look for whether or not he sees the words how far car went feet. And that's it in deciding whether or not to give you a point. Okay, so good news. There's not a lot of calculus in this calculus. Bad news, there's a lot of pre-algebra, and these questions are really easy to overthink and misread. Sometimes you just can't believe they just want the slope or base times height. Don't know if I went over enough to get you through the homework, but do your best. Should have definitely given you enough of an idea, but there are some tricks in each question, and we'll go over that. Do your best to try and do the last two free response questions at the end of these notes. All right, guys, I hope this helps. Hopefully I'll see you Wednesday. If not, hopefully Thursday. The snow will melt at some point, and I look forward to seeing you guys when it does. Email me with any questions, and hope to see you all soon. The good Lord willing and the creek don't rise.